In this series of videos, we're going to discuss concavity of a graph, and we're going to use the second derivative test. Now, there's a couple of things about the second derivative test that we're going to talk about. The first thing is we're going to work with that second derivative to discuss the concavity of a graph. And the concavity simply means the curving of a graph. The curving of a graph. Does the graph curve upward, or does the graph curve downward? Let's make that a little bit smoother. There we go. Downward. We'll know that a graph curves upward if the slope of the tangent line is increasing from left to right. Another way to tell is that all of these tangent lines are below the curve, or we could say that the curve is above the tangent lines. When the curve is above the tangent lines, that means from left to right. Here we've got a tangent line that's negative, and then here this second one, it's not as negative, okay, so it's not as steep. And then we have a tangent line that appears to have a zero slope, and then we have a positive, so we went from negative, not so negative, to zero, to positive, to more positive, right, steeper, a bigger positive number. So what's happening is that f prime is increasing. So the first derivative is increasing. Therefore, the second derivative is greater than 0. Okay? It's just like when f of x is increasing, right? Then f prime of x, that derivative that follows, is greater than 0. Same thing. If f prime is increasing, right? If f prime is increasing, then its derivative is greater than 0. So the second derivative is greater than 0. If you did not get that, don't be afraid to ask, okay? Or better yet, you could rewind the video and take it a little bit slower. When we have a concave downward graph, look at what our slope is doing. It's starting positive, then it's not so steep, still positive, but not so steep, then 0. So we're going positive, a smaller positive number, 0, and then negative, and then a bigger negative number, right? That means that our first derivative is decreasing. See, it's decreasing because it's starting positive and it's going to negative, so that first derivative is decreasing. If the first derivative is decreasing, then the second derivative is less than 0. Now, take a look at those tangent lines. Where are those tangent lines? Those tangent lines are above the curve, meaning that the curve is below the tangent lines. The curve is below the tangent lines. When the curve is below the tangent lines, you have a concave downward interval of your graph. So now here are the steps, and this is going to be the big part here, is just memorizing these steps and how do you go about doing the tests to find your intervals of concavity. First thing is that you want to find all the x values at which the second derivative is equal to 0. Notice how I'm saying all the x values. I'm not talking about critical numbers because critical numbers come from the first derivative. We want to find all the x values at which the second derivative is equal to 0, or where the second derivative is undefined. Okay, all of those x values are going to be used to determine our intervals. we're also going to use the second derivative and the sign of the second derivative. So test the sign of the second derivative in each interval. And I'm going to go one step further here. If f double prime of x is greater than 0, then you have concave upwards. Concave upward. If your second derivative is less than 0, then concave down. Okay, so that's really important. When you test the sign of the second derivative, positive is concave up and negative into the second derivative is concave down. Now the toughest part of this problem is going to be what we did in the last chapter. Okay, we want to find the second derivative of f of x equals 6 over x squared plus 3. So we're going to find the first derivative. The first derivative is going to be the opposite sign over x squared plus 3 quantity squared times the derivative of the inside, which is 2x. So we had to use the product rule there. And we know that that is negative 12x over x squared plus 3 quantity squared. Now we're going to find the second derivative. I'm going to use the quotient rule along with the chain rule. So the derivative of the numerator is negative 12 times the denominator, x squared plus 3 quantity squared, minus the numerator, negative 12x, times the derivative of the denominator, which involves the chain rule, all over the denominator squared. X squared plus 3 squared squared would be the fourth power. Let me clean this up a little bit. Negative 12 times x squared plus 3 quantity squared. And then I'm going to have plus, let's see, we've got 48. 12 times 2 times 2 would be 48. And then x times x would be x squared times x squared plus 3 to the first power all over that denominator, x squared plus 3 to the fourth power. So x squared plus 3, an x squared plus 3, and an x squared plus 3. I've got 3 terms in this fraction. I'm going to reduce them by dividing out that x squared plus 3 and canceling out, which is going to give me negative 12 times x squared plus 3 to the first power plus 48x squared all over x squared plus 3 to the third power. And that's going to equal negative 12x squared plus 48x squared is 36x squared minus 36 all over x squared plus 3 quantity cubed. Factor out the 36. And finally, we get our second derivative. Okay, take that in for just a moment. And then we're going to move it to the next page. So I'm going to copy and paste. If you need a longer moment, don't hesitate to pause and follow through this algebra. It is correct. I did not make a mistake. I have the same answer on my paper. Okay. So that process was this first step, setting that second derivative equal to 0. We also have to look to see if we have any undefined values of our second derivative. So I'm going to start with the undefined values of the second derivative. There are no undefined values. So I'm going to write that down here. there are no undefined values. There's no value that I can put in for x that's going to make that denominator equal to 0. No undefined x values. However, I can set this equal to 0, and I'm going to have a fraction equal to 0, and the only way that can happen is if the numerator is equal to 0. So therefore, when I set that numerator equal to 0, I'm going to get x equals plus or minus 1. So there are my numbers that are going to break up my domain of negative infinity to positive infinity and possibly change my concavity. I'm checking this into the second derivative, and that is equal to 36 times x plus 1 times x minus 1 all over x squared plus 3 quantity cubed, or 36 times the quantity x squared minus 1 over x squared plus 3 quantity cubed. We should agree that the denominator is always going to be positive. So this denominator will always be positive because any number times itself is positive, plus 3 will be positive, so our denominator will always be positive. If I put a negative, let's say a negative 10 in, I'm going to end up, might be easier right here, negative 10 squared is 100 minus 1 is positive. I'm going to have a positive over a positive, which is a positive. So this interval from negative infinity to negative 1 gives me a second derivative that is greater than 0. That's what that positive means. Then we're going to test the middle interval from negative 1 to 1. If I put a 0 in, I'm going to get a negative in the numerator over a positive in the denominator. That interval is negative, meaning that f double prime of x is less than 0. And then 1 to infinity, if I put a 10 in, once again, I'm going to get a positive over a positive, which is going to give me a positive interval, and that just means that the second derivative is greater than 0. So when that second derivative is greater than 0, I have a graph that is concave upward. So we're concave upward from negative infinity to negative 1, and again from 1 to infinity. And we're concave downward from negative 1 to 1. These are open intervals, so they're all parentheses, and that's our answer. So here's one for you to try. The math is very, very similar. Okay, I'm not changing up the entire problem. Math is very, very similar. We're going to have 12 over x squared plus 4. This way you can just try and do this one on your own. See if you can reproduce what I've done algebraically and using our rules of calculus. When you're ready to come back and check your work, press play. Okay, I've got f prime of x is equal to negative 12 over x squared plus 4 quantity squared, and then I'm going to have times 2x in the numerator, so that's negative 24x over x squared plus 4 quantity squared. My second derivative is going to involve the quotient and chain rule. So the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, which is your chain rule, all over the denominator squared. And squared squared would be the fourth power. So we'll have negative 24 times x squared plus 4 quantity squared plus 24 times 4 is 96 x squared times x squared plus 4 all over x squared plus 4 to the 4th power. Now this one is going to go away with one of these, which goes away with one of these. So we end up with, I can factor out, well, let's not factor. Let's make sure that you've got this. Negative 24, quantity x squared plus 4, plus 96x squared, all over x squared plus 4, quantity cubed. 96x squared minus 24x squared is 72x squared. Negative 24 times positive 4 is negative 96, all over x squared plus 4 quantity cubed. And if I factor that, I can factor 24 out, positive 24. And that's going to leave me x squared minus, I believe that is, that's not x squared minus, 24 goes in there 3 times. 3x squared minus 4, all over x squared plus 4 quantity cubed. Now, if you're turning this video back on and going, okay, yeah, I got that far, and then I kind of got stuck. These are going to be some different numbers. I've got no undefined values, so there's no x values for the second derivative to be undefined. Okay, so don't have to worry about that. But the numerator, I have to set that numerator equal to 0. So 3x squared minus 4 equals 0. That gives me x squared equals 4/3. So x is going to equal plus or minus 2 over the square root of 3, which is a little odd, right? So we've got this interval from negative infinity to positive infinity, because that's our original domain. And then we've got negative 2 over the square root of 3 and positive 2 over the square root of 3. That's a little bit more than negative 1 and a little bit more than positive 1. And we're going to check these into our second derivative. So if I put a positive, let's say a negative 10 in, I'm going to get a positive over a positive, giving me a positive. If I put 0 in, that's in the middle interval, I'm going to get a negative over a positive, that's negative. And if I put a positive 10 in, I'm going to get a positive over a positive, which is a positive. I'm putting my values into this second derivative right here. And I'm just looking at the signs. So we're concave upward from negative infinity to negative 2 over the square root of 3. And again from 2 over the square root of 3 to infinity. And we're concave down from negative 2 over the square root of 3 to positive 2 over the square root of 3. That one's a tricky one when it comes to the arithmetic and the numbers, because we are so used to looking at numbers and saying, okay, those numbers are just too weird for them to be right. So maybe I did something wrong. Not in calculus anymore. So when you get these numbers, as evidenced by, I think you took a quiz and you got something like the cube root of 7, and you probably know exactly what I'm talking about there. Yeah, you're going to get those numbers, and it's really challenging to make up problems or come up with problems where the second derivative ends up being perfect integers. So yeah, so that's our concavity. That's our concavity. So now what I'm going to do is I'm going to come back in the next video. I'm going to talk about the point of inflection and that second derivative test. That second derivative test, actually, you thought this was the second derivative test. This is just the second derivative to determine concavity. The second derivative test actually helps us find relative extrema. So in the next video, we're going to finish it all up by talking about points of inflection and that second derivative test to find relative extrema.